Welcome everyone to this explainer on the absolute fundamentals of software engineering. As your lecturer for this course material, I want to warmly congratulate you on taking this step. Whether you're aiming to build the next groundbreaking mobile app or design life-critical systems, mastering this foundational theory is absolutely crucial for your engineering careers. We're not just learning how to write code today, we are learning how to engineer robust, world-class systems.
Here is a quick look at our syllabus for today. We'll start with a welcome to software engineering, cover professional software development, the software engineering process, ethics and case studies, dependability and complex systems, and finally wrap up with a comprehensive course summary.
Okay, let's dive into this. Section 1. Welcome to software engineering.
Our modern society literally could not function without large, professional software systems. From national power grids to space exploration, software is at the heart of it all. But before we go any further, we really need to define our core term. When we say software in this discipline, we don't just mean the code. Software comprises computer programs and all associated documentation, libraries, and configuration data needed to make them actually useful. If you write a little personal script on your laptop, you might only care about the code. But professional software, that requires extensive documentation, user guides, and configuration files so that other engineers can use, maintain, and understand it.
Moving right along to Section 2, Professional Software Development. Now, what's really interesting about this slide is how it clears up a massive misconception. People often think software engineering and computer science are the exact same thing. Actually, they're not. As we contrast the fields, notice that computer science focuses heavily on theories and fundamentals. The underlying science of computation. Software engineering, on the other hand, is firmly focused on practical delivery. It's about producing useful software within real-world constraints like strict budgets and tight schedules. Think of it like this. Just as a physicist studies the laws of motion and a mechanical engineer uses those laws to build a safe car, the computer scientist provides the theory and the software engineer actually delivers the working product.
So when we build these products, who's actually in charge of what they do? Well, that depends on the category. Generic software products are your standard, off-the-shelf systems, like a word processor or a photo editing app. The developer controls the requirements and builds it for a broad, open market. Then on the flip side, we have bespoke or customized software. This is built specifically for a single client. Think of an air traffic control system or a highly specialized dental records database. In this case, the customer dictates exactly what the software must do.
But regardless of whether the software is generic or bespoke, all good professional software shares 4 essential attributes. First up, acceptability. The software must be acceptable to its intended users, meaning it's intuitive and usable. Second, dependability and security. It has to be reliable and safe, ensuring it doesn't cause damage if it fails. Third, efficiency. Good software must always minimize waste. It shouldn't hog system memory or drain a battery unnecessarily. And finally, maintainability. It must be written in a way that allows it to evolve over time, because trust me, requirements always change.
That brings us to Section 3, the software engineering process.
To achieve those high standards of acceptability and dependability, we rely on a structured framework. Let's move to the actual process and see how this builds together. Every software process, no matter the specific methodology you use, involves these 4 fundamental activities. First, specification. Defining exactly what the software needs to do and setting its constraints. Second, development, designing and writing the actual computer programs. Third, validation, rigorously testing the software to ensure it actually solves the customer's problem. And fourth, evolution, modifying and updating the software as market and user needs naturally change over time. This systematic approach leads us right to the formal definition of our entire field. Software engineering is an engineering discipline concerned with all aspects of software production, from initial conception to operation and maintenance. I really want to emphasize that phrase, all aspects. It's a highly managed process. It goes far beyond just sitting down in a dark room and typing code. It includes project management, quality assurance, tooling, and high-level strategic planning. Let's jump into Section 4, Ethics and Case Studies. Because we are building systems that deeply impact human lives, we have to look way beyond our technical skills. So the crucial point is,
Being a professional means accepting that your job involves wider responsibilities. Your behavior must be guided by ethics. You have to recognize and uphold incredibly high ethical standards. It's not just about what you can build, it's about honesty, integrity, and understanding the social and legal impacts of the systems you deploy. If a system you're working on is unsafe, you have a professional, ethical duty to speak up.
To truly grasp why ethics matter so much, take a look at this embedded software system for a portable insulin pump. We can see the blood sensor that actively reads the patient's current condition. That data flows right into the central controller, which runs our software. The controller processes this data and sends a signal to the pump to deliver a very specific dose of insulin from the reservoir right through the needle assembly. If the software in this controller fails, the pump could deliver a fatal overdose. The patient's life literally depends on our code.
And this brilliantly illustrates how we translate that physical hardware into software logic using a UML activity model. We see the blood sensor taking a reading. The software analyzes this reading to compute the exact blood sugar level. It then checks the insulin log, computes the necessary insulin dose required, and finally translates that into direct pump commands. Every single step here must be validated rigorously. A misstep or an unhandled exception in this flow, that could be completely disastrous.
Now on to Section 5, Dependability and Complex Systems. When lives are on the line, like with that insulin pump, how do we actually engineer for total dependability? Well, we must look at the big picture, socio-technical systems. These are overarching systems encompassing hardware, software, and human operational processes. You just cannot analyze the code in isolation. An engineering failure in any one of these elements, whether a physical hardware sensor breaks, the software has a bug, or the human operator simply misunderstands a warning screen, can lead to catastrophic overall system failure. When analyzing these systems, engineers have to categorize risks. On one side, we have intolerable risks. These are direct threats to human life. Going back to our insulin pump example, a massive insulin overdose is a completely intolerable risk. As engineers, you must prioritize preventing these at all costs, designing fail-safes so they literally cannot happen. On the other side, we have ALA-RRP risks, which stands for as low as reasonably practical. These might be less serious hardware glitches that could cause, say, a minor delay, but won't physically harm the patient. We minimize these as much as our budget and schedule practically allow, but intolerable risks always come first. Managing all this risk is getting harder every day because we're increasingly building systems of systems, megasystems of massive complexity. You cannot analyze a large-scale system merely by looking at its individual parts in a vacuum. Complexity creates what we call emergent properties, behaviors and reliability issues that only emerge when all the hardware, software, and humans interact dynamically. Because a tiny change in one database can cascade into a massive failure in a connected subsystem, how we manage the human element of this complexity is absolutely vital. Because these systems are so incredibly complex, the way human engineers communicate is crucial. I want you to flag this specific number for your exam prep, 4 to 6. That is the ideal software engineering group size. Why? Because keeping teams to 4 to 6 members drastically reduces communication bottlenecks. In a massive project, you don't just put 200 people in a room and hope for the best. You break them down into highly coordinated small teams of 4 to 6 to maintain clarity and control over all that complexity. Finally, we arrive at Section 6, Comprehensive Course Summary. We've covered a tremendous amount of ground, and I want to formally congratulate you on reaching the end of this course material. Let's tie it all together. The glossary of this discipline isn't just a list of words. It's the shared language of professional software engineers worldwide. Look at Theme 1, Process. Terms like Waterfall model, Agile methods, and Scrum remind us that software isn't just coding. It's a heavily structured process. Then look at Theme 2, Quality and Management. Terms like configuration management, quality management, and refactoring remind us that writing code is only the very beginning. Professional code must be rigorously maintained, reviewed, and controlled over years of evolution. And then we have Theme 3, Architecture. Client-server, component-based design pattern. Building software is exactly like building a skyscraper. It requires a brilliant architectural blueprint before you lay a single brick. And for your upcoming job interviews, knowing this professional vocabulary is what separates junior coders from true engineers. You absolutely must know the difference between validation, which means checking you are building the right system that the customer actually wants, and verification, which means checking you are building the system right according to the technical specs. Knowing terms like continuous integration inside and out is key. The software industry moves at an incredibly fast pace. The frameworks and languages you're using today, they might be totally obsolete in 10 years.
But I want to leave you with this final provocative thought. How will you apply these foundational principles to the fast-moving future of software engineering? The concepts of total dependability, ethical behavior, striving to always minimize waste, and using structured processes, those are timeless. They will guide your entire professional career no matter what new technology emerges next. Thank you so much for joining me in this explainer, and best of luck in your amazing engineering journey ahead.